If you've ever taken a course in electrical engineering or electronics in general, then you've probably heard this analogy before. Electrical current is like the flow of water. A battery is similar to a pump that just moves electrons around. Wires are like tubes. Resistors are like choke points that constrict the free flow of electrons. Capacitors, well, those are just big tanks full of sloshing electrons. Inductors are, well, let's not worry about inductors for a minute. The analogy is a fun little teaching toy. It's easy to understand on a very basic level and doesn't really hold up when you move into more advanced topics. But what if you really riffed on the whole hydraulic analogy? What if you took things to their logical conclusion and actually, made one of these hydraulic circuits? You can actually do just that. At least it works for many electrical components. You can quite easily model a circuit just using tubes full of water or compressed air or really any other kind of fluid. All you have to do is make sure your fluid restrictions are the right size and everything is pumped at the right pressure. You should even be able to create your model accurately enough to run calculations on it. The hydraulic analogy can actually be quite quantitative if you get down to it. But can we go further? If we use the hydraulic analogy to model circuits, we should be able to model just about anything, right? Can we model math? Can we even, perhaps, build an entire computer using nothing but tubes? That has to be too far-fetched, right? Welcome back to Advent of Computing. I'm your host, Sean Hass, and this is episode 86, Fluidic Computing. Today, we're going to be looking at one big question. It's one that keeps me awake at night and one that I keep coming back to. What even is a computer? Of course, we do have a guiding principle thanks to Alan Turing. The generalized definition boils down to a machine that can execute conditional branching. A true computer has to be able to compare values and then change its execution based on the outcome of that comparison. That's worked well as a goalpost for modern machines and for modern programming languages, but I think it breaks down a little bit once we look at the historical context. This general guideline, called the Turing Completeness Theorem, doesn't really work for analog machines. It also doesn't work well for some mechanical computers. So, when we start going back to the dawn of the digital era and even further, we need to get a little more loose with our definitions. This episode, we're going to be diving into a computing technology that's obscure, strange, and outside the well-defined Turing-complete realm. We're talking about water and fluid-based computers. And that is right. That is actually a thing. So let's start by breaking down the completeness theorem and, well, removing its biggest requirement. Never mind the whole reacting based off comparisons thing for a second here. A computer has to have some way to represent numbers and some way to operate automatically on those numbers. The automatic bit here, I think, is crucial. You need a computer that can automate away some work. Otherwise, it's just a calculator. Now, you could say that computers really just automate math, or if you want to be philosophical, you could say that a computer simulates human mathematics. Current digital computers are boring, since they represent numbers as a series of discrete electrical pulses. You get on and off, 1 and 0, lame and more lame. Some analog machines represent data as rotation of a drum, which is a little more interesting, has more of a cool factor. Going further afield, we get to the Fluidic Machines. These computers store numbers as volumes of water. We're talking encoding via milliliters here. That is far cooler than ones and zeros. As far as operations go, well, that follows directly from this very flexible encoding scheme. It's possible to perform mathematical operations on these vats of fluid using pumps, pipes, and valves. As far as automatic, look no further. Equations can literally be modeled as the flow of a fluid through pipes. Now, jokes aside, fluid-based machines can actually implement many of the features of their more solid counterparts. In fact, if carefully constructed, they can implement every feature that a normal run-of-the-mill electronic computer has. But do they have any advantages? Well, that gets a little murky. Today, we're going to be taking a very broad survey of fluidics. This broad approach is partly due to sourcing. There aren't exactly volumes and volumes written about water calculators. I also think that this will give us a pretty well-rounded foundation for understanding these strange machines. To that end, we're going to be looking at 3 computers in particular: Moniac, the Water Integrator, and Flodac. Between these machines, I think we should be able to draw some conclusions. Why would you want to use fluids to model mathematics? How do fluidic machines relate to the larger field of computing? And finally, the subtle one, do these strange machines tell us anything about the human drive towards computers? This is a question that I tend to mull around in my head. After looking at the sheer diversity of machines that have been built, it kind of makes me wonder if it was inevitable that us flesh folk would look towards some more hard, automated counterpart. I know that may sound a little poetic, but it's a serious idea to consider. Were we somehow pre-wired to build computer-like machines? Or are computers just so simple that we keep reinventing them? Now, before we get into the actual show, I want to just slip in one quick announcement, if I may. I happen to know the producers, so I think he'll let me get away with it. I'm currently working on a project that's being tentatively called Notes on Computer History. It's going to be something between a magazine and an academic journal discussing the history of computing. Now, my big goal with this is to provide an accessible venue for people to write about their research in computer history. I don't want this necessarily to be a place for just academics. I want it to be a community project that a lot of people from many different backgrounds and different skill levels can contribute to. The impetus is there's not really a place for that right now. I mean, there are academic publications that discuss computer history, but those are hard to get into. You have to go through a peer review process, for instance. So Notes on Computer History is going to be an accessible place where all of us have a chance to contribute. To that end, I'm looking for contributors. Right now I have a few people that have already said they'll help me do editing for submissions, but I could still use some more editors. If anyone listening is good at typesetting and LaTeX, I could use maybe 1 or 2 more people that know LaTeX besides myself on the team. And more than anything, I'm looking for submissions. So if there's something about computer history you're interested in, or something you've been looking into, maybe a neat machine you've run across, then please get in touch. I'd love to feature you in this magazine. You can reach out to me on Twitter at adventofcomp, or just email me directly. I'm adventofcomputing@gmail.com. I'm planning, once I get a domain for this project, to have a fancier email, but right now, just send something to my personal email and we'll talk. I'll get you in touch with an editor. With that quick announcement out of the way, let's get into the actual content for today. To start with, we need to talk about economics. We also need a disclaimer. I am no economist. I don't know which theories are correct, and I don't really know that much about the field, so please don't send me hate mail if I malign your favorite or chosen school of economics. Rest assured that I don't exactly know what I'm talking about. With that said, let's talk some economics. Specifically, we need to talk about 2 economists, William Phillips and John Maynard Keynes. The last name here is probably the most familiar. Keynes is the progenitor of the so-called Keynesian school of economics. Now, this is all outside my usual area of expertise, but as I understand it, immediately after the Depression, Keynes published a hot tract called The General Theory of Employment, Interest, and Money. This would become the foundation for his tradition of economic theory. The general idea is that markets should be well regulated in order to flourish, and that small fluctuations on the micro scale can build up and lead to fluctuations on the macro scale. One final piece to note is the employment part of Keynes' general theory. The text deals, in large part, with how the rate of employment ties into other economic factors. Another thing to keep in mind, just in general about economics, is that it's something of a flexible science. It's not entirely a hard science, it doesn't work from first principles like math or physics, but it's also not a totally soft science like history, for instance. It's somewhere in between. Economics tends to use math as a way to describe very human-driven processes. It's the last bit here that adds in some mushiness. The point is that economics can, in fact, benefit from calculations. At least mathematics can make for a guide to navigate that mushy human factor. At the most, that can be used for quantitative purposes. Different schools of economics will tend to have different uses for mathematics or maybe interpret equations in a different way, but numbers are key here. The fancy word, if you want to sound impressive, is model. As in, why yes, this all conforms to my latest model. In general, a model is just an equation that's used to represent some phenomenon or system. The game Oregon Trail, for instance, uses a model to calculate how food is consumed during a trek. In that example, a model is used to simulate a phenomenon, to figure out what's happening at any given step. You need some way to calculate how much food you have once you reach Oregon in the first place. Models can also be predictive. That's the more exciting type of mode for economists, say. The ability to model and then predict economies. As long as your model is sound, then there's no reason you can't just run it forward a week or maybe even a year. The Keynesian school of economics rose to prominence after the publication of The General Theory. It garnered many followers, and the theories and models laid out by Keynes were expanded over the years. One of these devotees was the other economist I mentioned, William Phillips. He got to economics via something of a circular route. You see, Phillips was initially trained as an electrical engineer. Phillips was born and raised in New Zealand back when that country was still held by the British Empire. Quick throwaway fact about our main man Bill here. At one point, he worked as a crocodile hunter. So, needless to say, he had a mixed background. Phillips eventually found his way to the UK, where he was trained as an electrical engineer via a correspondence course. This was just prior to the outbreak of World War II. After the war, he returned to the UK and resumed his education. Now, there's something here I want to highlight. That's the danger of multidisciplinary studies. Of course, I mean threat in the best possible way here. Phillips had initially been fascinated by engineering and electronics. Here I'm drawing from the book Electric Brain, The Stories from the Dawn of the Computer Age by Mike Hawley. The text has a chapter covering Phillips' exploits. Hawley chose to start that passage by describing how Phillips, a teenager at that time, fixed up a dead car so he could get to school more easily. From there, things sort of snowballed. Like many others, Phillips was profoundly changed by the Second World War. He fought for the British first in China, then in Java, all the while fleeing the advancing Japanese troops. Phillips was eventually captured, becoming a prisoner of war, but his engineering savvy wouldn't rot away in some prison camp. Phillips would work on a number of clandestine radio sets that were cobbled together with the help of his fellow inmates. Hawley also relates how Phillips built a tiny electric stove for boiling tea. Tiny creature comforts like this were one way to survive the horrors of internment, but also must have been used to keep Phillips' mind sharpened. We don't know the specifics, but during this period, Phillips seems to have become interested in organized human relationships. I say that we'll never know the specifics here because, in general, prisoners of war don't talk much about their experiences. I have a little bit of a personal connection here too. My grandfather was also interned in Japanese prison camps during the Second World War. He very rarely and very reluctantly discussed his internment with the rest of the family. It's an experience one wants to forget. When pressed, Grandpa would bring up light anecdotes like swapping a watch with a guard for a bottle of beer, but he never really gave us the full story on anything. It appears that Phillips was much the same. So we have a few anecdotes, a few small details about the better moments, but we don't have the full story. Hawley's chapter on Phillips was constructed primarily from interviews with those who knew Phillips personally. From that, Hawley suggests that Phillips was intrigued by the social connections formed between inmates. After the end of the war, Phillips returned to England and, armed with this new fascination, enrolled in a sociology program. So, evidently, a bit of a transformation occurred. However, he quickly realized that he wasn't all that interested in sociology itself. Part of his degree program involved taking a general course in economics, and it was at this lower level class that he found his true new passion. Heather Sutton, one of Phillips's classmates, describes the transformation like this, quote, "We were walking around Lincoln's Inn Fields one day, and he explained to me that he had realized that economics was just simple hydrodynamics, and he proceeded to wave his arms around and tell me all about it. Not that I knew anything about hydrodynamics, but he really engaged my attention, and I never forgot that meeting." End quote. Specifically, Phillips had become engrossed with Keynesian economics. The hydraulic analogy here does seem pretty sound. Economic models usually represent how funds flow from one category to another. In the Keynesian school, that flow is controlled and restricted by some regulatory agency. You might be describing how money flows out of your wallet into things like rent, food, and internet hosting fees. All the while, a small trickle is diverted off for taxes. In a traditional model, that flow would be expressed as an equation. Something like total expenses equals tax rate times the sum of rent, food, and services. That works great quantitatively, but it has some conceptual issues. The equation on its own represents a relationship which is pretty abstract. If you plug in values, then you get actual results, but you only get one snapshot in time. Maybe the result is $50. That might be a cool value to look at, but it doesn't really describe how the relationship works. It doesn't provide much understanding. Another option is to generate a graph of the model. For this, you need to pick your variables. A 2D graph, the kind you can draw on a chalkboard, will have one free variable. So you might end up needing a number of graphs in order to show how expenses change as each category fluctuates. That's not all that intuitive and possibly time-consuming for more complex models. The hydraulic point of view that Phillips stumbled on offers a totally new way of representing this model. Plugging in every number to that model gives you a discrete value, $50. Plotting a graph gives you something more like continuous values, a curve or a line. The hydraulic model gives you something entirely different. It shows a fully dynamic representation and, depending on how you set things up, allows you to inspect different aspects of that model in real time as they change together. Here, we see the threat of interdisciplinary studies reach its full bloom. It's something that shows up surprisingly often in my coverage. Someone will have a background in one field and interest in a second and go on to do great things. A diverse background tends to, in my admittedly amateur analysis, open a person up to new and unique ways of thinking. For Phillips, his engineering background gave him a new insight into economics. It also drove him further. If this hydraulic modeling was a passable theory, then why not build a machine? It sounds like these fluidic dreams had come to Phillips near the end of the school year. He was already kind of done with sociology. He'd been slacking in order to draft plans for a strange device. Once school was out for the summer, he set to work. In his landlady's garage, he started building a strange machine. A fascinating point here is that Phillips had already secured a little bit of funding. An economics professor had seen the value of this hydraulic model, so kicked in some money to help construct the device. His landlady also provided some funds. From what I've read, it sounds like Phillips had a sort of magnetism to him. He was able to make people believe in his ideas. The machine he built would be christened Moniac. As folklore goes, it was a joke on the name ENIAC, which had been recently unveiled. As far as the timeline goes, this does check out. Phillips constructed Moniac in 1949, about 4 years after ENIAC came to life, so there's plenty of leeway in there for him to hear about the more real computer. Specifically, Moniac was designed to model the English economy, at least initially. It was a simulation of the Keynesian view of macroeconomics. In that sense, it was a series of equations modeled via the flow of water from tanks. That all sounds pretty simple. In practice, it's also relatively straightforward. But the trick is getting everything to flow around just right. Moniac consisted primarily of a set of tanks connected by tubes. Now, I want to approach Moniac as if it were a computer. That's going to be a primary assumption here. And by computer, I just mean a machine that represents numbers and automatically operates on them. So forget the whole comparison business. The reason to take this framework is that it gives us a nice list to move down while discussing Moniac's technical features. It will also make it easier to point out its idiosyncrasies, I think. So let's start with a very basic rundown of the machine. Moniac was composed of clear tanks and clear tubes, plus a pump and a few valves. Dyed water started out in a reservoir at the bottom of the machine, which represented the total market you were modeling. A pump carried that water up to the top where the fluid flowed down under gravity. All the stuff in the middle, all the paths for the working fluid, represented the model. Looking at how Moniac handled numeric representation gets us, well, into some weird territory pretty quickly. Phillips had built an analog machine, so we get some baggage here. In general, analog computers represent data as continuous values. You don't have a distinct 0 and 1. You have a rotating shaft that can represent any possible value between 0 and 1. Results of calculations also exist in this continuous state. As your gears grind, you'll see physical movement. Dials will sweep through multiple values on their way to a final answer. Certain numeric values in Moniac were represented as the water level in small tanks. These were particular values of interest. A 2007 article by Chris Bizzle called The Moniac, a hydromechanical analog computer of the 1950s, provides some insight on the machine, plus useful diagrams, which, when you're dealing with analog computers, is very important. As Bissell explains, these tanked values were significant variables in economic models. Moniac could be set up in a few different configurations, but the most documented was a simple simulation of national economies. That's the model that I'm working off here. This specific model had variables for income taxation, surplus balances, Federal Reserve, domestic expenditures, foreign held balances, and the ominous International Monetary Fund. You know, all the usual fields you might have in your household budget spreadsheet. These were all variables that could be monitored. numbers that could be read out and watched for changes. Call them registers if you want to make the comparison to a modern computer. However, some numbers were represented as flows. For instance, there's a big pipe at the very top of Moniac labeled taxation. That is a variable that would show up in an economics model, in a mathematical model specifically, but it's not a measurable value for Moniac. These flow or piped variables are constants in the actual equations. Many of them are also adjustable probably before Moniac starts running. I think if you moved a valve, that might upset the model's integrity. The taxation tube, for instance, can have its flow restricted by a valve. So this is still a type of numeric representation, it's just more of an input than an output, if that makes any sense here. Numbers were operated on by the simple flow of water downward through these labeled tubes, but there were some catches that modified that flow. Some tanks would drain freely. The Federal Reserve tank, for instance, was allowed to flow free. Phillips also implemented these interesting proportional flow slots. These are tapered slots that restrict the flow out of the tank such that they drain at a rate proportional to their fill level. They look like slim pyramids. If I understand correctly, then the more full the tank is, the higher the flow rate. Some valves in Moniac were coupled to floating switches, which acted as water level gauges. The idea here was to create feedback that would change how freely water flowed through certain tubes. In this economic model specifically, imports are affected by domestic expenditures and foreign-held balances. Accordingly, there's a valve on the imports tube that is opened and closed by corresponding floats in the proper tanks. In other words, Moniac hits all our key points. It had a way to show numbers, kinda. It operated on those numbers automatically. That's pretty close to a computer as far as I'm concerned. There's even a small element of feedback and choice in there. Moniac could also create a data product. Phillips would later expand Moniac by building plotters that connected to a series of floats. That way the value of variables could be recorded. But here's the thing. Moniac is sometimes called a computer, but it wasn't ever a serious computer. It's not a big suit and tie kind of machine. The first outing of Moniac was a demonstration, but not as a hardcore calculating device. No, Moniac was always designed to be used as a way to visualize economic models. You could call it a teaching aid, but I have some problems going that far. Moniac was first shown off at a seminar at the London School of Economics. The crowd was composed primarily of grad students and professors. The machine wasn't being used as a teaching aid to show first-time students how economics worked. It was positioned more as a way to visualize a complex system. This was a difficult task given the state of the art in 1949. Phillips claimed that Moniac was accurate within a few percent of mathematical models, but this machine wasn't really producing quantitative results. The computer was more a way to aid in a qualitative understanding. Ultimately, a number of Moniacs were actually built in varying configurations. It proved useful in this economic education niche. But this isn't the end of the episode. We can keep going down this weird fluid rabbit hole. What if we actually wanted to produce quantitative results using water? Well, it has been done. We just need to go a little further back in time. To get into this truly wacky hydraulic world, we need to head to the USSR in the 1930s. In general, it seems the computing developments behind the Iron Curtain are somewhat unknown in the West. Of course, I have to give an obligatory shout out to my friend Kristaps over at the Eastern Border podcast. He did an episode on Soviet computers a while back. It's a good show to check out. Anyway, this obscurity becomes doubly true once we get into the era of analog computers. I mean, American analog computers are pretty darn obscure to Americans already. Part of this lack of coverage comes down to accessibility. Analog machines work on totally different principles. The language barrier makes studying Soviet analog computers especially difficult. But luckily for us, some of the suits over in Washington have translated a few documents. This is actually where the story gets even weirder. In the early 50s, the Army Corps of Engineers was looking to build a hydraulic analog computer of their own. Yeah, this technology isn't a one-off thing that Phillips dreamt up. We'll get back to the provenance of this translation later, but I want to get to the actual document first. Vladimir Lukianov was working in construction during the early era of the Soviet Union. More specifically, Lukianov worked as an engineer for the National Rail and Road System. During this period, the late 1920s into the 30s, the railroad was rapidly expanding. The state in general was rapidly industrializing, which demanded more infrastructure. But there was a weird problem: cement. I know, once again, I bring you the mundane parts of history. But my friend, that's really what computing is all about. Here's something you've probably never thought about. Cement doesn't always cure evenly. Different parts cure at different rates. Interior regions cure differently than exterior regions. And these rates are all affected by temperature. Now, in some situations, this isn't a big deal. Each chunk of a sidewalk doesn't have to harden up at exactly the same time. But if not accounted for, this unevenness can spell doom for cement structures. Think bridges, tunnels, foundations, and even roads. Uneven curing can, in some cases, lead to cracks that weaken overall structural integrity. So, your bridge might look great, your pylons are all set, the roadbed is being laid. What would happen if one of your pylons had cured inconsistently? Maybe the shape that was chosen didn't allow for internal regions to harden or dry or heat up at the same rate. There's a gradient somewhere. A small stress forms. That could cause internal cracks, and those cracks could propagate, leading to a disaster. The temperature component here is especially insidious. The USSR covered a massive region of the planet, from warm coastal waters in some southern regions to some of the coldest parts of the world up in Siberia. A concrete structure might cure just fine down in Odessa, but in Vladivostok, a cold winter might make your cement crumble. These kinds of integrity issues aren't always immediately noticeable either. It might take months, years, or even decades for anything to actually go wrong. The way around this situation was to design structures and mix cement in a way to minimize cracking. But that's not all that easy. Surprisingly, this involved a lot of math. If you know much physics, you may have spotted the red flag here. I mentioned temperature. That means this is a thermodynamics problem. For those uninitiated lucky few, thermodynamics is one of the nastier parts of physics. The math involved is frustratingly complex. You end up needing to handle vector math, and you end up running a lot of partial derivatives. If you don't know what that means, well, let me just put it this way. The math involved takes a lot of work. This is especially true when you need to solve thermodynamic equations. For instance, if you want to try to figure out what temperatures will cause a slab of cement to crack. That's not just plugging in numbers, that's rearranging and then plugging in numbers. It's a small difference, but it ends up making things a lot more complicated. Lukianov's solution was to automate the process. Now, I'm working with limited documents, so I'm not entirely sure where Lukianov got this idea. I don't have a diary entry from the Lukianov papers, for instance, that explains everything nicely. That said, I have some details from a translation of an article in the Russian journal Science and Life. According to that piece, Lukianov was drawing from earlier analog computing efforts in the USSR. The big connecting fiber here would have been the work of Mikhail Viktor Kirpichev, and I'm sorry for all the mispronunciations. Kirpichev was a physicist who developed a method that Lukianov called the hydraulic analogy. Or, at least, Kirpichev laid the groundwork for this analogy. So, what exactly is the hydraulic analogy? This is going to be based off my physics degree plus my somewhat tight-ish grasp of Lukianov's machine. Let me start by introducing you to a cool little equation. PV equals Nrt. This is a nice equation that chemists seem to really love and is also applicable to any fluid dynamics work. It states that pressure and volume are directly proportional to the number of moles of a fluid and that fluid's temperature. Moles, in this case, are just a way to measure the amount of a substance, and the R here is a constant that makes the numbers work out. There are a few ways to read this depending on what you're interested in, and it only holds for certain substances that don't care about compression, but we're not going to talk about that. That's a go take a chemistry class kind of discussion I don't want to have. Here's the reading that matters for concrete and water. If pressure and number of moles are kept constant, then a change in volume is directly proportional to a change in temperature. If the substance's volume goes up, then its temperature will go up a proportional amount. The opposite also holds. Here's how this becomes useful. Using this equation, you can turn an equation that cares about temperature into one that cares about volume. In other words, you can make a thermodynamic equation into a volume-dynamic equation, or whatever you'd call that. I guess hydrodynamic? Anyway, you can turn a model that talks about temperature into one that talks about volume. That's the gist of this equation. What makes the Lukianov paper a little hard to parse is that he gives most equations in terms of a variable h. That represents the height of water in a tube, or the height of a column of water. That works out to something that approximates volume. Just put a pi and a size of the tube somewhere near it. What you end up with is a set of equations that relates a change in the height of water in a column to a change of temperature in another system. It's a neat little math trick, and if you like this kind of stuff, then might I recommend taking a few physics courses. This is the theoretical foundation for Lukianov's water integrator. It follows from there that the central element of this machine would be vertical tubes filled with what else but water. Technically speaking, the translated paper doesn't say explicitly that it's filled with water, so it could be something else, but come on, it's probably water. So we're in a similar realm to Moniac, but there are notable differences in the principle of operation. Both Moniac and the water integrator represent numbers as the height of water. Call it volume to be technically accurate. The water integrator is grounded in more generalized mathematics, while Moniac was built for a very small set of applications. I'm going to be focusing on the one-dimensional water integrator since, as complexity goes up, the machine gets much more difficult to understand. Lukianov did build 2- and 3-dimensional machines, but those are a little above my pay grade for right now. Besides, the 1D solution is just easier to explain in audio form. For this to make sense, I have to touch on one more math thing. Sorry, but this is going to be the last of the math. The class of equations that Lukianov was dealing with are called differential equations, specifically partial differential equations. That is to say, equations that include derivatives. These express the change of certain values over the change of another value, aka the slope of a curve. Think of something like the change in volume over the change in time, for instance. Lukianov wanted to solve these, which means an integral, hence the name water integrator. The device was physically integrating equations. Now, the integral is really just a way to calculate an area under a curve. There are calculus proofs that show how the integral is how you reverse a derivative, but I can leave that as an exercise for the reader, so to speak. To numerically solve an integral, as in the way computers handle it, you have to break a curve down into chunks. If you're integrating against the variable x, for instance, then you might call these chunks delta x, as in a little change of x. It'll give you some cool street cred if you do so. For each of these chunks, you then calculate the area under the curve in that region. Then you add up each chunk to get the total area. Lukianov's integrator does this in a very visceral manner, and I just dig it. Each delta x is represented by a single glass tube. As water enters the integrator, these tubes fill up to the proper height. Taking the sum of those heights gives the total integral. If you just look at the height of water in each of these tubes, which are set side by side, then you can actually see the slope of the curve. You can see a nice little curve, any shape you want. It's really neat to see diagrams of this. Now, the actual curve and the value under it are two useful data products right there. And remember that height of water is equivalent to temperature, so this is actually solving a thermodynamics problem just with water. I can't stress how cool that is to me. Of course, the actual machine is more complicated than just filling some tubes. Just like with Maniac, there are contrivances used to fill in the details of the model. One interesting aspect of the integrator is its system of floats. This is a system of adjustable rubber tubes and small floating outlets that help keep the actual readout tubes from emptying past a certain point. This allows an operator to set a lower bound for each delta x. The integrator also has a way to model resistances. I'm not talking electrical resistances, but temperature resistances. Each layer of concrete in Lukianov's model will have some resistance to the transfer of heat energy. Thanks to PV equals Nrt, this can be modeled as hydraulic resistance. In other words, little tubes that make it harder for water to flow. To set up a model properly, small glass tubes had to be inserted between each of the vertical readout tubes. These came with different levels of hydraulic resistance that had to be matched up carefully with the mathematical model. The final bit of fun are the so-called Prismatic Inserts. The name is kind of cooler than the actual device. These are pieces of metal that are curved on one side and tapered on the other. These prismatic inserts are, well, inserted into the vertical readout tubes. This allows an operator to adjust the cross-sectional area of the tube to correct for temperature change. Remember that temperature must remain constant for the whole equivalency thing to hold. From this, I think it's clear to see that the water integrator was a very serious scientific tool. As for the actual use of the integrator, well, that gets a little tricky. This is where I hit that sourcing barrier again. I'm dealing with scant translations here. There are some sources, but I don't trust them all that much. I've seen it mentioned that versions of Lukianov's machine were used up to the 1980s, but I don't have primary documentation backing up that claim. The actual truth of the matter is probably in some untranslated scientific papers. That said, I can't believe that the water integrator would have seen use into the near modern era. Many pre-digital technologies were in use up into the 1980s or 1970s more conservatively, only dying out with the rise of commodity microcomputers. It helps that the water integrator was doing something slightly different from mainframes and other big iron machines. Real silicon and electron computers, at least ones that existed prior to the rise of PCs, filled a different niche. Lukianov's integrator was operating like a really fancy desktop calculator, while big computers were better for more complicated research or operational tasks. We can also factor in resource contention here. Some vacuum tube machines were used well into the Silicon era because there simply weren't enough computers around. Everyone needed computer time, but resources just couldn't allow for that. If you were working in a Soviet lab and just needed to run some integrals, then it may have been hard to get access to a fully fledged computer. However, there was a more hydraulic alternative kicking around. I guess this brings us up to a lead that I've kind of been keeping buried. Why is there a translation of Lukianov's article anyway? I mentioned that the translation was part of an Army Corps of Engineers contract, but there's a bigger story here. You see, the Corps of Engineers wanted a hydraulic computer for their own, possibly shady purposes, or maybe cool. This is part of a larger series of projects called, quote, Frost Investigations. It's a good name for a coded operation, perhaps. Anyway, the main goal was to model how the ground freezes and thaws. Turns out that model is very, very close to the concrete cooling model that Lukianov was cracking back in the 1930s. But the rabbit hole gets deeper and stranger. To quote from one of these Frost investigations, apparently hydraulic analog computers originated almost simultaneously in the United States and in Russia in 1935 and 1936. Moore built and patented an apparatus which he called a hydrocal for the solution, principally of heat flow problems through building walls. At the same time, Lukianov built a hydraulic apparatus in the Russian Institute of Roads and Construction, which he used to study a variety of problems, including freezing in soil. End quote. The Moore in question here was Professor Arthur D. Moore of the University of Michigan in Ann Arbor. His machine operated on the same principle as Lukianov's, but had a slightly more complicated construction. His readout tubes could tilt in order to change their cross-sectional area. So, once again, water-based computing isn't some one-off invention. I gotta add in one more weird wrinkle. This is a part of Lukianov's report that, when I read it, kinda shocked me. It kinda messed me up a little bit. It's easy to fall into this mind trap where you see analog computers as evolutionarily separate from digital computers. I mean, what does an IBM PC have to do with a pile of wet tubes? Admittedly, not a lot, but there is a through line. Lukianov's translated article that I've been working off was published in 1939. The history of the concept of Turing completeness is a little complicated. There are precursor theories that are similar. There are earlier machines that exhibited similar properties. Turing starts describing so-called Turing machines in the late 30s into the 40s. That's where the idea of Turing completeness really comes from, very broadly speaking. So it's possible that Lukianov read about Turing, but I think that's somewhat unlikely. Turing was a math student, Lukianov's an engineer. They're related fields, but they're different journals, and maybe even a language barrier. Keep this in mind as I read this quote from Lukianov's 1939 paper. Quote, "The author believes that, in some cases, the hydraulic method can even be extended to problems beyond the limit of equations. Undoubtedly, the principles of this method permit a very wide application to problems, but in order to realize these possibilities, it is imperative to be able to create a machine which can be applied to several kinds of problems, instead of to just one." The water integrator was just modeling a single equation. It could be reconfigured, but fundamentally it was always solving a derivative. It was always running an integral. It was tied to this world of very concrete mathematics. To get past that, you need something more algorithmic. A machine with the ability to follow instructions, adapt, and solve multiple types of problems. You need some generalized machine. To crib from only slightly later works, you need something like the universal Turing machine, a device that follows simple instructions, operates on data, and can solve any type of problem. Lukianov even goes on to describe how his water integrator could break past equations if it could dynamically change while it was crunching numbers. That, my friends, sounds an awful lot like a Turing complete machine. In this small passage, we can see that even back in the analog days, researchers wanted more. Better still, they basically knew what they wanted. It wasn't just some, ethereal, I wish this machine was better. No, they want computers very specifically. Lukianov is stating quite plainly that it would be much better to build a machine that can go beyond math. In other words, a machine you can program, a fully fledged computer. For me, that goes a long way towards establishing some ideological line between a pile of wet tubes and an IBM PC. Both machines are striving towards the same dream. One just happens to be further along the path. Now, if you'll permit me, I'm going to make the story even more strange. This one is to go further beyond, so to speak. So far, we've been talking about analog computers that existed prior to digital machines, or just around the advent of recognizable computers. What about after the digital boom? What about, say, after the transistor? Surely the fluid-based computer was done once transistors arrived, right? Let me introduce you to a little machine called Fluidic, designed by none other than Univac themselves. The year 1964. Stranger still, Fluidic is described as a binary computer. That's right, binary doesn't have to be electric. Now, just a quick disclaimer. Fluidic isn't strictly a water-based machine. The final model ran using compressed air. That said, all the theory that makes Fluidic possible would work with any fluid. So, what I'm getting at here is that water binary computers are, in fact, very possible. Everything we know about Fluidic is relegated to a single paper. This article was written by 3 Univac employees, R. Gluskin, M. Jacoby, and T. Reeder. As far as I can tell, this is their only publication, which is a bit strange. The paper in question, Fluidic, a pure fluid digital computer, was published in the American Federation of Information Processing Society's Proceedings. Big mouthful, but that means that the computer was either shown off at a conference or there was at least a talk about the computer. Someone knew about Fluidic. Someone had to. There just isn't much chatter outside of this one paper. Source complaints aside, this is advent of computing after all. The Fluidic paper offers a fascinating alternative to boring electronic digital machines. Better still, the authors actually present a very persuasive argument. The core of any electronic digital computer is the triode. That's a specific type of amplifying component that takes 2 inputs and gives a single output. Back in the day, these were vacuum tubes. Those were replaced with transistors, and those were eventually replaced with doped silicon. This means that, at least in theory, anything that can be used as an amplifier can be used to create logic elements. From there, you get what I like to call the big computing-proof backdoor. If you can create certain types of logic gates, then you can plug your work into the larger body of computer science proofs. Usually, you need either a not and gate, aka NAND, or a not or gate, aka NOR. You can build an entire computer using only NAND gates or only NOR gates. And like I mentioned, there's a lot of proofs showing how that's done. So if you can get up to that step, you win. You're done. There are quite a few ways to construct basic triodes, but most of the well-known approaches are electronic. It turns out you can construct an analogous component for fluids, using some careful geometry and basically nothing else. These are called fluid amplifiers or fluidic amplifiers. In principle, they're really similar to electronic amplifiers, but, they don't really care about electrons. So a normal electronic amplifier works kind of like a valve. You have some large input current that is then switched by the signal you want to amplify. This allows you to control a larger current with a comparatively weak signal. These are called triodes because they have three legs: the input, the trigger or signal, and the output. The output leg is where you get the amplified signal. Fluidic amplifiers do the same thing, but just for fluids. You have an input port that takes a strong current, like a jet of water. Then you have a trigger or gate port that accepts a weaker signal. You then get an amplified signal out your output port. One of the neat things about these fluid amplifiers is that they have no moving parts. The input current is physically deflected by the incoming signal, and both of those currents, are just fluids. Usually this is done by placing the signal jet perpendicular to the input jet, and then carefully shaping the output nozzle. That redirection is called momentum transfer and allows a relatively weak stream of fluid to redirect a much stronger stream. There is one other fun effect that we can work with: the wall effect. A fluid stream can get stuck, for lack of a better word, on a nearby wall under certain circumstances. This all depends on geometry, but in general, you can trap a stream on a wall. The stream can then be unstuck if it's given a push in the correct direction. That sounds a lot like memory. The Fluidic paper starts from this point: fluidic amplifiers and a few basic principles, and builds from there. The first stop is actually an inverter, a NOT gate. This is a fluid component that will invert inputs. Once again, this is all accomplished using basic geometry, just like with the basic amplifier. The actual NOT gate is a channel cut in a block of some material. The final component operates just like a normal electronic NOT gate. Putting in a 1 will output a 0 and vice versa. It's just that in this case, a 1 is represented as a pulse of fluid and a 0 as the absence of fluid. From there, the paper builds up a few more gates before we hit the big one, the NOR gate. The geometry here is a little funky. It's a weird asymmetrical Y with a little V stuck to the side. I'll link to the actual article so you can see it yourself, since I can't really describe it very well. Anyway, we're up to the NOR gate. Thus, we've reached the magical proof back door. We're approaching a computer. And here's where UNIVAC really delivers. What follows is what I can only describe as a digital fever dream. Fluidic was never meant as a very powerful computer, let's just say. It's a tech demo, a proof of concept. A model was actually built, and that's what the paper describes. Fluidic was composed of around 200 fluidic NOR gates. As I've mentioned before, the working fluid wasn't water, but instead compressed air. In theory, you can use any fluid. Air just turns out to be the most convenient in this case. Each NOR gate was injection molded plastic. The physical implementation is a little odd, but once we get away from that, Fluidic is remarkably mundane, if small, for a computer. Let me lay out the machine a little just to drive that point home. Fluidic has only 4 instructions: transfer, add, conditional jump, and halt. Those instructions were encoded as binary numbers with arguments also as binary numbers. Data was represented in binary. Immediate working data was stored in an accumulator register. More data, as well as the actual program, was stored in random access memory. The actual memory bank was tiny, FLODAC only had 4 words of storage available, but hey, it's a research machine, so it can be forgiven. This is, by all measures, a computer. The conditional jump even means that it fits the whole Turing definition. Now, that's all very run-of-the-mill. We have a digital machine that executes instructions and encodes data as binary numbers. Getting to the inputs and outputs drops us back into the more fluid territory. The input panel is probably my favorite part of the whole machine. Instead of switches, FLODAC uses a series of bleed holes. These are just holes that air normally rushes out of or bleeds off pressure. To actuate these holes, you block them with your fingertips. That causes pressure to build up and a flip is flopped somewhere. This means that to input data to FLODAC, you play it just like a recorder or a penny whistle with a series of holes that you seal with your fingers. There's something whimsical about that I just love. Output is where we reach the only moving part of FLODAC proper. Data is displayed via a series of clear tubes with little plastic balls inside. If there's air flowing into the tube, aka a 1, then the ball's pushed up. Otherwise, the ball stays down. So for the entire computer, the only actual moving parts are a few small indicator beads. That's pretty slick. Now, that's the computer itself and the theory. It's a neat machine, but it leaves us with one big question. Why? Why exactly build a fluidic computer? The authors over at Univac actually have a 4-part answer that I find fascinating. To quote, reliability, environmental immunity, low cost, and absence of RF radiation, end quote. The low cost part is kind of the least interesting, but I think it's worth addressing. The argument goes that since each logic element is just injection molded, a computer like FLODAC could be made really cheaply. In general, you could use any material to build one of these fluid machines. You just need to mold specific shapes, or engrave. You can use any manufacturing process that can make the properly shaped channels. I don't think this rationale has really aged super well. FLODAC was designed back in the 60s when a computer meant something very different from a modern computer. The same year the FLODAC paper was published, 1964, for those keeping track, IBM unveiled their System 360 series of machines. These computers cost hundreds of thousands of dollars. With inflation, some models would have been past the $1 million mark. The idea of a computer built from cheap plastic parts would have been really exciting. But nowadays, we have the microprocessor, which fits the bill for cheap, reliable computing without requiring some new operating principles. Reliability and environmental immunity offer more interesting justifications. In theory, a fluidic computer could operate indefinitely. I really want to underline that indefinitely part. This is thanks to the fact that you can use any combination of material and fluid to build these machines. Just pick a hard material that can't be eroded by the working fluid and you're done. You have an unkillable machine. The only failure point would be a compressor or some kind of pump needed to circulate fluid, but clever design can solve that. Something like a pulsar pump can move water using gravity alone, and it has no moving parts. So, in theory, the entire device could be static, no moving parts at all. As far as environmental immunity, this stems from that same design flexibility. A normal computer is limited to conductors and electrons. Sure, you can choose exotic conductors, maybe get some germanium up in there, but you fundamentally have to be pushing electrons around. Conductors tend to interact with things like heat or acidic compounds. Copper, for instance, will corrode and melt relatively easily. Metals will melt at high temperatures. Metals also lose conductivity at higher temperatures. Temperature cycling between hot and cold can cause cracking in certain materials. These are definitely edge issues, but they do matter for things like space-bound computers. A satellite could be subjected to extreme cold and extreme hot, swings between those temperatures, plus the vacuum of space. For that reason, computers used in space are often specifically designed for that use case, or heavily protected. But with fluidic computers, you get to pick all materials involved. You can make a machine with tungsten elements that uses liquid gallium as a working fluid. You could use some type of heat differential pump to move around the liquid metal. The machine could withstand temperatures in excess of 2000 degrees centigrade. That machine could, in theory, survive being submerged in magma. Good luck dunking an IBM System 360 into a volcano. That won't last very long. Fluidic computers are also immune to another silicon killer, radio frequency radiation. That's another huge problem for space-based computers. Radiation plays havoc with traditional machines. More specifically, radiation can induce charges in conductors. It can also damage certain materials. Fluidic computers, depending on the materials used, are actually impervious to radiation. These machines don't rely on electrons like electric computers do. Radiation? Who cares? Another small note here is that traditional electric computers also create RF radiation. It's just a product of moving currents down wires and through junctions. Since fluidic computers don't deal in electrons, they don't produce radiation. Once again, this helps make fluidic computers almost inert objects. This really captures a certain sci-fi feeling I get about fluidic computers just in general. FLODAC fits into something like the computer science uncanny valley. It's binary, functions like a normal computer, but does all its work using compressed air and pipes. It stores numbers as a gentle breeze and runs calculations using a series of tubes. It makes the mind real. One of the reasons that I'm so taken with FLODAC comes down to the possibility of extraterrestrial life. And hey, I see you out there. Stick with me. I swear I'm going somewhere with this. I've been a bit of a space nerd for most of my life. I mean, I do have a degree in astrophysics. During undergrad, I also interned at the SETI Institute, so I do have some inside baseball knowledge about the search for ETs. It's kind of a underlying passion of mine. As we're reaching the end here, I want to introduce a bit of a spooky idea. It's called the Fermi Paradox. This paradox is relatively simple to lay out. It's obvious that life must exist outside of Earth. There are various ways we can reach that conclusion, most of which come down to the fact that the building blocks for life exist in abundance all over the universe. Add in the age of the universe, and we arrive at the fact that life must have also evolved elsewhere in the cosmos. That's kind of just a fact. If you disagree, then it's the podcast's stance that you're kind of wrong. So if life exists out there in the ink, then why haven't we made contact? Why haven't we seen concrete evidence of extraterrestrial life? That's the paradox. There are a number of solutions ranging from aliens just don't like us, up to most worlds wipe themselves out via war before they can travel the stars. One of the factors that SETI stresses is that alien life forms probably communicate in a way that would be unrecognizable to us Earth folk. I personally like that idea, that there are alien signals out there, we just can't make sense of them yet. Much of the search for aliens comes with assumptions about their environment and technology. A habitable planet should be something like Earth. It should have liquid water. It shouldn't be bathed in radiation, and the civilization there should emit some kind of radio signals. Any civilization advanced enough to, say, build computers should be sending data around as RF radiation. Sans that, there will at least be some electronic signature, right? Some techno signature, as it's called. Well, what if humans are the odd ones out? What if we just happen to be more obsessed with electrons than other life forms? I'm sure someone could write a whole book about how our situation on Earth has informed this obsession. Maybe it's the elements present on the planet, or the fact that our eyes see in a particular part of the spectrum, or maybe even the heat of our local star. I bring this up to point out that maybe, just maybe, a world exists out there where the local apex predator doesn't really care about electrons. Maybe they're more interested in the flow of fluids. So hey, let's just pick a planet and flesh out some details. Let's go with Venus. It's hot and has a thick atmosphere, so that blocks a lot of light and causes intense pressure at the planet's surface. The Venusians never evolved eyes like ours. There just isn't much to see, and the arid atmosphere would dry them out pretty quick. The population lives underground in grand cities. They had an industrial revolution, but it didn't end in electronic power, since they didn't need lights for their underground homes. Maybe at one point they even experimented with gear-based computers, but those fell out of fashion once binary became the way of the future. The Venusian Industrial Revolution required a lot of math, so eventually a grand calculating machine was devised. It used convenient materials, pressurized carbon dioxide and volcanic glass. The glass channels were, of course, made via injection molding. It's all built on an assembly line after all. These alien fluidic computers could work off the same principles of binary logic we use on Earth, but used no conductors, no semiconductors either. They wouldn't produce any recognizable signals, no signature that we could glean. Let's say millions of years pass by, society on Venus has crumbled or maybe they left. Earthlings finally land on the planet. Any metallic machines have long since corroded away, or at least ceased to function. The only record that's left is stored in the Grand Venusian Computer, a giant cavern filled with intricately molded volcanic glass. If we came face to face with this kind of machine, how many computer nerds would think, oh yes, I've seen this before? We definitely couldn't detect its output from space, even as the computer was still crunching away. Religious site. Alright, that does it for our very literal exploration of the flow of data. I think we've charted the breadth of fluid-based computers in this episode. From the wishy-washy demos of Maniac to the brass tacks of the water integrator, and then onto the uncanny valley that is Flodac. At the end here, there are a few small details that I want to highlight. I think it's important for us to all remember that electronic digital computers offer just one mode of computing. A machine doesn't have to be built that way. It just so happens that the current state of the art uses binary logic represented as currents on wires and semiconductor junctions. Computing has seen a lot of variety over time, and I think it will see a lot of variety in the future. The current regime, the microprocessor world, only came about in the mid-70s. That's barely 50 years old. Who's to say what the next 50 years will bring? Maybe it won't be fluidics, but we should keep our eyes peeled for left-field solutions. This sort of connects up to my big philosophical question this episode. Was the creation of the computer inevitable? Were we somehow predestined or predisposed to build automatic number crunchers? I mean, just look at the sheer number and variety of computing machines that we've made over time. Fluidic computers offer a great example of the lengths people will go to in order to automate math. In this instance, I think the water integrator is the best possible example. It shows how something as mundane as tubes of water can be used to solve physics equations. If you'll allow me the indulgence, I'm going to get a little out there with it. The fact that we can model physics with devices like the water integrator points to some kind of satisfying symmetry in the world. As soon as we figured out physics, we started looking for ways to exploit physics. On one end of the spectrum, we have binary computers, a very abstract way to model physical phenomena. On the other hand, we have analog machines like Lukianov's water integrator, a very direct approach to calculating and modeling. For me, it seems like as soon as physics became a consideration, we as a species were on a crash course for computing. just the ability to manipulate and swap around equations that describe the world, well, that can really start you thinking. To me, I think it can lead us Earthlings to some very interesting places. Thanks for listening to Advent of Computing. I'll be back in 2 weeks' time with another piece of computing's past. And hey, if you like the show, there are now a few ways you can support it. If you know someone else who'd be interested in the history of computing, then why not take a minute to share the show with them? You can also rate and review on Apple Podcasts. If you want to be a super fan, then you can support the show directly through Advent of Computing merch or signing up as a patron on Patreon. Patrons get early access to episodes, polls for the direction of the show, and bonus content. You can find links to everything on my website, adventofcomputing.com. If you have any comments or suggestions for a future episode, then go ahead and shoot me a tweet. I'm at adventofcomp on Twitter. And as always, have a great rest of your day.